for you. You get to do that. So in case you missed it, I know you guys didn't miss it because if you weren't in class, you already watched the video. But just in case, I made some important announcements last time. Mostly that the class changed from now on, so there's not going to be a long homework 5, but instead this is the first of the short homeworks. Okay. I'll send you guys an email with all this information, but you should know that this is the first short homework. It's due next Friday, which is what, May 10, I guess. April.
May 25. You can do that.
And no class. April. Today's the 1st, right? So 3rd, 6th, and 8th. We're on spring break. Okay. So we were talking about Borel-fixed monomial ideals. So we said that an ideal in a polynomial ring is Borel-fixed. Well, so by definition, this is just that it's fixed by the action of the Borel subgroup, right? So this is what it means to be Borel-fixed. And we said that this is the subgroup of upper triangular invertible matrices. Okay. But I gave you kind of a sketch of a proof of a more combinatorial description of what these guys look like. So equivalently, I is Borel-fixed if two things hold. The first thing is that it should be a monomial ideal. I is a monomial ideal and the second condition is the following. If I have a monomial in I, and I have some variable that occurs in it, so let me call it xj, and I have some smaller variable, let's say I less than j, then I can always replace in my monomial m, I can take out the variable j and put in, or I should say, I can take out one occurrence of the variable j and put in one occurrence of the variable I. The way I do that is by multiplying by xi over xj, and this should be in the ideal. Okay. So this is one of the main things that we did last time. Okay. So the first thing that I wanted to tell you today is I wanted to show you a way in which these Borel-fixed ideals occur very naturally. So Borel-fixed ideals occur in nature, let's say. And here's one way in which that happens. Let's say that you start with any ideal. You have any ideal, and you have any monomial ordering. Okay. So we already talked in much detail about what happens when we look only at the leading terms of the ideal with respect to this monomial order. So we get this initial ideal, right? The ideal, the monomial ideal, generated by the initial terms of all the polynomials in I. Okay? Well, what I want to tell you is that basically there is a way in which we might get accidentally the wrong answer here. But let me tell you what I mean by this. The thing is that we could also see what happens when we do the same procedure, but not for this ideal, but for basically the same ideal under a linear transformation. Okay? So suppose that instead we first perform a change of variable, which we said is what happens when you act by a matrix. Okay? So suppose that we first performed a change of variables in other words, we act on our ideal by a certain matrix, which is the matrix of change of basis. Okay? So then what we do is that we get something that we call GI. Okay? And let's suppose that now we take the initial ideal, but we do that after this change of basis. Okay. So you see what I'm doing? I'm taking the ideal that I started with. Now I'm going to pick some random invertible matrix, and I'm going to change the variables according to what that matrix tells me to do. So then now instead of my ideal, I'm going to get some new ideal, a different ideal, GI, and then I take its initial ideal. Okay? So let me show you an example of what I'm trying to do here. So maybe the ideal that I had here was generated by x1 squared and x2 squared. And let's suppose that my order was the lexicographic order with x1 is greater than x2. Okay? And I do this. So what's the initial ideal with respect to this term order? Well, we know that this takes some work to get it. I mean, we know that if we start with a general ideal I, what are we supposed to do? What we're supposed to do is basically compute a Grosvenor basis. Right? But here it's actually fairly easy to just see this manually. Of course, this polynomial lives in I, and its initial term is itself, right? So that means that x1 squared lives here. Okay? This polynomial lives in I, so its initial term is itself. And so we get this guy. And now if you think about this, all the other terms that live in I are given by x1 squared times some polynomial plus x2 squared times some polynomial. Right? And that means that everything that occurs in this ideal has to have one of the variables square. Every term has one of the variables square. So if it is x1 squared, then the initial term is generated by this guy. If x1 doesn't appear, then it's generated by this guy. Okay? So you can kind of reason your way into believing that the initial ideal is just this. Okay? So we get that answer. But let's say that now we do what I'm telling you to do here. And let's say that I do it for a matrix like this one, maybe. Okay. You'll see that for some reason I have the habit of sometimes putting matrices in a square instead of in brackets, but I hope this is not too unsettling. It's just the same thing. Okay. So what happens when we do this? Well, what I'm supposed to do is take each one of the generators that I have over there and act like this matrix. Okay, so I let G act on x1 squared and I let G act on x2 squared. Okay. What does this do? Well, remember what I'm supposed to do is G tells me do a change of variables where now your first variable is given by the first row, your second variable is given by the second row. So the first variable is now x1 plus x2, second variable is x1 minus x2. Okay. So what happens here is that this x1 now becomes x1 plus x2. And x2 now becomes x1 minus x2. Okay. So this is the ideal that I get. And we should ask ourselves, well, is this the same ideal? Is it a different ideal? Let's figure it out. So let me just multiply this out. So my ideal looks like this. And now if I look at this, I see that I can generate x1 squared plus x2 squared, right? And I can generate x1, x2. Right? If I add these two guys, I get 2 times x1 squared plus x2 squared. If I subtract them, I get 4 x1, x2. And remember that I assumed throughout this whole discussion that the characteristic is 0, which means that I can divide by 2, I can divide by 4. Okay? So I get these two guys, and so this is my ideal. Okay? And now we can see that actually we did change the ideal because, for example, x1, x2 lives here, and x1, x2 does not live here. x1 squared lives here, and x1 squared does not live here. Okay? And so let's just take now the initial ideal according to the lexicographic order with x1 bigger than x2. Okay? So the initial term of this guy is x1 squared. Right? The initial term of this guy is x1, x2. And now am I done? Well, it depends whether this is a Grosvenor basis or not. And this turns out not to be a Grosvenor basis. Okay? So if you were to do this carefully and compute a Grosvenor basis, you would see that you're missing something else. For example, let me show you a polynomial that lives here. x1 squared plus x2 squared times x2 minus x1 times x1, x2. Okay? So of course this is in this ideal because of the way that I'm writing it. What I get is x1 squared x2 minus x1 squared x2 plus x2 cubed. Okay? So x2 cubed lives in this ideal, which means that its initial term, which is x2 cubed, lives here. Okay? And again, if you do this carefully, you'll see that this is a Grosvenor basis once I have added this x2 cubed, which means that this is my initial ideal. Okay? And I got some different answer. And maybe that's not too surprising because so far there's no reason to believe that we should have gotten the same answer. Okay? But here's kind of the punchline of what I want to say. The punchline is that if I asked all of you guys to choose a different matrix G, and you don't get to see what the person next to you is doing. Each person chooses a matrix G at random, computes G acting on I, computes the initial ideal, then I'm willing to bet that at least 12 of you would get the same answer, and maybe 1 or 2 of you wouldn't if you chose the identity matrix, for example, or something silly. But the point is that if you choose a random enough matrix, you're always going to get this answer. This is not obvious, but it's true. Okay? Actually, I think this is very strange. I find it hard to believe, but it's a theorem. So, proposition, most, and I'm going to say what I mean by most here, most choices of G give you the same initial ideal. Okay. What do I mean in this case, in this example? In this example, the initial ideal of, if I chose the matrix A, B, C, D, then you're always going to get this answer. Unless AC is equal to 0. Okay. So basically, what I'm saying is probably if I asked you guys to choose random matrices, most of you would not put a 0 here or here. And if I know that you didn't put a 0 here or here, then I know you're going to get the same answer. And by the way, if you did put a 0 here or here, then I know for a fact that you'd have gotten this answer. So there's only 2 possible answers, which are this one and this one. Okay? And in most cases, you get this one. And this is the theory in general. Okay? And so, since most of the time we get the same answer, then we give that guy a name, and that guy is called the generic initial ideal. Generic initial ideal, and it's denoted GIN of I. Okay. And this is why I was telling you that in some sense you can think of this as, when we took this initial ideal, it was kind of accidental that we got this answer. But under most changes of coordinates, we should have gotten that answer, and maybe you can think of that as the morally correct answer somehow. Okay. So this has a proof, but like I told you, we're going to do a lot fewer proofs now, and I'm not even going to send you to Miller-Sternfels because they send you somewhere else. So I think this is a, I should have looked this up, but I think this is a theorem of Bayer and maybe Stillman. But, well, if you go to Miller and Stonefels, then they'll tell you where to go. But that's a fact. And by the way, so now hopefully this homework makes sense. In this homework, what I'm asking you to do is, here you have some ideal, a fairly simple ideal, and now I'm asking you to, under all possible changes of coordinates, you're going to get just a finite list of possible answers. In this case, there were only 2 answers. Right? Most of the time you get this one. If you have an accident, you will get that one. And here, again, you're going to get a finite number of answers, and so I'm asking you to basically tell me what those answers are. Find all distinct monomial ideals, initial ideal Gi as G runs over GL3. So over all invertible matrices G. Yeah?
So here you said that there are only 2 possibilities.
Mm-hmm.
In general, is there a form to find if you have the same variables, there'll be distinct possibilities?
So the question is, there were only 2 possibilities. How are you, for example, here, how are you supposed to know when to stop? There is not a general theory, but it is true that there are a finite number of answers. This might be a good question for you to think about, actually. How many answers? If you can give a bound on the number of different possibilities that you might have. I don't know of any results in this direction, but it is true that there's always a finite number of possible answers. So at least you know that this homework ends. And it is but it's not so bad, actually. In principle, this list could be huge, but this one is not so huge. That's why I chose us a simple ideal. Okay, so this is a very nice ideal, generic initial ideal, and maybe you can see where I'm headed. Theorem. Oh, I guess actually this is proved in Miller and Stonefels. What is not proved is that this guy is Borel-fixed. For the lexicographic order. Okay. And this is the one that's a theorem of, I did write it down. I don't know if I'm supposed to say this in Spanish. Gallego, Bayer, Gallego, and Bayer, Stillman. So I think you'll agree that I mean, basically what I'm telling you is, for any ideal in your polynomial ring, there is kind of a morally correct generic initial ideal, and that guy is Borel-fixed. So that means that these Borel-fixed guys really arise very naturally. This is a good reason to study them. Okay. Any questions about that? Okay. So you remember that I started last time by telling you that the reason we were going to talk about Borel-fixed ideals is the following, that we already understand monomial square-free ideals fairly well. Right? We know that monomial square-free ideals correspond to simplicial complexes, and we know the very close relationship between the algebra of the ideal and the topology and the combinatorics of the complex. The next question was, what do we do if I'm not monomial? And I told you basically that's a hard question in general, but that's kind of what will occupy us for the next month. And this is the first example where we can say something nice. So these Borel-fixed ideals are not necessarily monomial, as you can see there. These guys are not monomial ideals. But it turns out that we can, for example, write out their Hilbert series very easily. And so that's the next thing that I want to do. But maybe I'll just say it. So the nice thing is Borel-fixed ideals have simple, explicit Hilbert series, many numbers, free resolutions. And this is kind of the punchline, really. That even though they're not monomial, they're still very nice. Okay? So I think what I'm going to get to do today is prove for you a formula for the Hilbert series, and then I'll just indicate the other stuff. Okay? So to get a proof for the formula for Hilbert series, I'm going to need a small lemma. Okay? So it says this. It says, suppose that I is a Borel-fixed ideal, and suppose that. So remember that the way this goes, because Borel-fixed ideals are monomial, they have a unique minimal set of generators. You guys proved this, that monomial ideals have a unique set of generators, and if you remember when we thought of monomial ideals as little dots, then the generators were kind of the corners of this diagram. For example, we said that this thing right here corresponds to saying, okay, well, x1 squared is over here, so these guys live in my monomial ideal. x1, x2 is over here, so these guys live in the monomial ideal. x2 cubed lives over here, so all of these guys. And so these are all the monomials that live in my monomial ideal. And I have a unique set of generators, which is given by the lower corners. Okay? All of those guys are essential, and I need them. So let me give names to those guys. So let's say that M1 up to MR is the minimal set of generators. Okay. So what I want to say is that then every monomial M in I can be written uniquely as M equals Mi times some M prime, where the largest letter occurring in Mi is less than or equal to the smallest letter occurring in M prime. So what I'm saying here is that for every single monomial that lives in this Borel-fixed ideal, there's going to be one particular generator that's going to claim it. It's going to say that's my M is my monomial. Okay. M can be written as that Mi times some other stuff, where all the variables in this other stuff are greater than or equal to all the variables that occur in Mi. And what I'm going to do is I'm going to do a proof by example, and I think that way with the example you'll see what the statement means, and then you'll also see why it's true. So let's do it for this guy. This guy is supposed to be Borel-fixed according to the Gallego-Bayer-Stillman theorem. And of course, you can also just check that it's Borel-fixed by checking for each monomial. if you take out a bigger variable and put in a smaller variable, then you should stay in the ideal. So that's true. And now let's take some monomial that lives in this ideal, like this one, for example. Okay. And somehow I need to write this guy as one of these generators times some other stuff that's bigger. Bigger in the sense that all the variables that appear are bigger. Okay. So here's how we can do it. Maybe you can already see how to do it. And if you, sorry, what happened with that? I wanted to do a different example, which is more interesting. Here there's not a lot of interesting thing happening. Let's do this example, which was our example in the last class. Okay. I want 3 variables so that we can see some stuff happening. So maybe you can see how to do this already. So if you do, pretend that you don't. Okay. Because what I'm going to do is the following. I want to write M as a generator times some other stuff. Okay. Now, this M lives in the ideal, right? And that means that I can definitely write it as a generator times some other stuff, by definition, because I am in the ideal. So let me do it in some random way. Let me, for example, say, well, this guy is a multiple of this guy. And this is how it's a multiple. Okay. So this is M3. And then this would be my candidate M prime. So now I have to check if this condition is satisfied, that the largest variable appearing here is less than or equal to the smallest one that appears here. And that's not true, right? For example, you can see that I have an x3 appearing here and an x2 appearing here. And that's not supposed to be, because all the stuff in this side should be less than or equal to all the stuff in this side. Okay, but then what I can do is the following. I can say, let me take an x3 out of here and put it over here, and let me take an x2 from here and put it over there, and just rewrite this equation as x1, x2, x3 squared, and x1 squared, x2 squared, x3. Okay. So all I did is take a true equation and then just substitute an x2 for an x3 and move them, switch their places. Okay. So what can I say now? What I can say is that I obtained this monomial by taking something in the ideal and taking out x3, adding x2. I took a bigger variable and I added a smaller variable. Because this guy is Borel-fixed, when I do that, I'm still in my ideal. So when I do this thing is still in my ideal, because this ideal is Borel-fixed. This thing is in the ideal. So if this guy is in the ideal, then I can write it as a multiple of one of the generators. And so I do that. So for example, x1, x2, x3 squared can be written as x1, x2 times 3 squared, where this is a generator, right? This guy is, sorry, I guess this was M4, right? And now this guy is M2. It's the second generator. So I get x1, x2, x3 squared, and x1 squared, x2 squared, x3. Okay? And now I have a new way of writing M as one of the mi's. In this case, it's M2 times some other stuff. Okay? And now I check again. So now I check, can this serve as my M prime now? So to know that, I have to see whether each variable here is less than or equal to each variable here. But again, that's not true, right? Because here I have an x2, and here I have an x1. And so then I repeat this process. Okay? I can take this equation, switch the x1 and the x2. So all I did is I switched these guys places. Again, I say this guy lived in my ideal, so when I switch a bigger variable for a smaller variable, this must be in the ideal. So because it's in the ideal, it must be generated by somebody. Okay? And I see who this guy is generated by, x1 squared. Well, in this case, x1 squared is one of the generators. So what I get is just m1 times x1, x2 cubed, x3 cubed. You just write it like this. Okay? And now again, I have a new candidate for an mi. I have a new candidate for an m prime. And again, I check. Does every variable here less than or equal to every variable here? And now it is. Here I have 1, here I have 1, 2, and 3. And that means that now I satisfy this condition. And so I can let my algorithm stop. Okay? So the way that I'm doing this algorithm, I just say, just take your m, generate it in some random way by one of the mi's, let the other stuff be called m prime, and see if that expression mi times m prime works. If it works, you're finished. If it doesn't work, it's because two variables are out of place. So switch those two variables. And when you do that, you're going to get a new candidate for mi, a new candidate for m prime. And you just keep repeating this until you're done.
When we're saying less than equal to, it's not our usual lexicographic order. It's less than.
That's right. So when I say here less than or equal to, I mean that the subindex of this guy is less than the subindex of this guy.
Right.
Like I have here. So it's the opposite convention of the lexicographic order that I put here. From here to here? I did remove it, so I had an x1 squared, and then I got just an x1. So I just removed one of them. I put in one x2. I moved one x2 from here to here, and one x1 from here to here. So, by the way, why does this end? Because we're improving at every step, right? So one way of saying that is that there are several ways of saying this, but for example, when I go from M4 to M2 to M1, I'm always making these guys smaller in terms of the biggest variable that appears and the power that it appears to. Here the biggest variable that appeared was x3 to the third power. Here the biggest variable that appeared was x2. Here it was x1. So I keep improving my situation, so that means that eventually this has to stop because I can't keep descending forever.
So in general, the best algorithm, do we take your variables from large, or your generators from large to small
Yeah, exactly. So, so this is why I told you that if you could already see right away how to generate this m, then you should pretend that you don't know, because if you kind of step back, you'll realize that what I did was really stupid, right? I did it in exactly the wrong way. Because I said, well, I want to generate this m, and let me generate it in some random way, but I generated it in the worst way, which is making this guy the biggest possible. Really what I should have done, and what you want to do, is do it with the smallest guy possible, and that's the end result of this algorithm. But I wanted to give you the proof that this algorithm always works. But now if you actually want to do it in practice, you would start over here. For that. So this proof by example shows existence. I mean, this shows that every monomial can be written uniqueness is not hard, but I'm going to skip it because I don't have much time left. So this you can see in the book. But more than this, what I want you to think about is really that I like the wording that I used, which is the following: every monomial gets claimed by a unique mi. Okay? So for every one of the monomials, you're either going to correspond to m1, to m2, up to mn. Okay? The point is that I want to compute my Hilbert series, so I want to figure out what all the monomials are. And the way that I'm going to count them is I'm going to first count the ones that use m1, then count the ones that use m2, etc. Okay. I wonder if I can even draw a picture for you. What's the example that I didn't do? x1 squared, x1, x2, and x2 cubed. Okay. So what are the monomials that live here? Well, I wish I hadn't erased this, but we can do it again, right? So x1 squared lives here. x1, 2 lives here, x1, x2 lives here, and x2 cubed lives here. Okay. So these are the monomials that live here. So what I'm doing is that I'm distributing all these different monomials in 3 classes. What are the ones that I associate to x1 squared? Well, it's x1 squared times anything, right? Because any m prime works here. I can use anything for n prime. And so that means that these guys all of these guys are going to correspond to x1 squared. I color them black. Okay, they correspond to x1 squared. What are the monomials that correspond to x1, x2? Well, if my mi is x1, x2, then my m prime cannot use x1, right? Because mi uses x2, so that means that m prime can only be a power of x2, which means that I can only take this guy and multiply it by powers of x2. Okay? And so these are going to be the monomials that correspond to x1, x2. And if my mi is x2 cubed, then again, I'm not allowed to use x1 for my m prime, and so that means that these guys get to be blue. So what I'm doing is that I'm separating all my monomials into 3 groups. The black group corresponding to the black generator, the brown group corresponding to the brown generator, and the blue group, which looks kind of black, but this is blue, corresponding to the blue generator. Okay? This is a picture of this lemma. And then actually, it's very easy from this picture to write the Hilbert series of the ideal. Because I just do it group by group. For example, what is the sum of the blue guys? The guys corresponding to the ideal x2 cubed. Well, it's x2 cubed plus x2 to the fourth plus x2 to the fifth. In other words, what I'm doing is taking x2 cubed and then allowing myself to put any power of x2. So let me write this in blue because these are the blue terms. Okay. Then what about the brown guys? Well, all the brown guys are multiples of x1, x2. And what you get to do is put x1, x2, and then put some power of x2. So this is the sum of the brown monomials. Okay. And now, for the black guys, all of them are multiples of x1 squared. And now, you can put in any monomial in x1 and x2, which means you just choose whatever power for x1 and choose whatever power for x2. So that's the formula. And this same formula works for any one of these guys. It looks like this. So here's the theorem. If I is generated by all of these guys, and these guys are the minimal set of generators, and if the maximum variable occurring in Mi is maybe, we'll call it Ui, then the Hilbert series of my, oh, so I should say this is Borel-fixed, right? So if this guy is Borel-fixed, and if the maximum variable occurring in Mi is Ui, then the Hilbert series of my ideal is given by, again, the idea is the same, that you're going to have one term for each one of the mi's. Okay. So you get sum from I equals 1 to r of what? Well, in the numerator, we just get the generator, right? So the numerator here was x2 cubed. Here it was x1, x2. And here it was x1 squared. Okay. And in the denominator, basically what you're allowed to do is use any variables that are greater than or equal to this one. This is the smallest variable that can appear. Okay. So here the biggest variable that appeared was x2, so you only get x2. The biggest variable that appears is x2, so you only get x2. The biggest variable that appeared is x1, so you get x1 and x2. So if the biggest variable that appears is ui, then you're going to get to multiply everything between ui and n. And that's it. So the way you prove this is you kind of carefully do the same color argument that I did. But you see that what this means is that computing this Hilbert series is very, very easy. Right? If you have a Borel-fixed ideal, then all you have to do is figure out what the minimal generators are. And then for each one you get a term where the numerator is just the monomial, and the denominator is just a very predictable power of 1 minus xj. So it just goes from ui to n, and ui is immediate to read from mi. So that means that the Hilbert series is extremely explicit. So that's an idea. That's basically a proof of the Hilbert series. And like I said, if you think about these things a little bit more carefully, you can extend this so you're able to compute not just the Hilbert series but all the Betty numbers, and actually the minimal free resolution, which in this case is called the Eliaho-Curvaire resolution. Now, because we don't have a lot of time left, instead of trying to rush through that, what I would like to tell you is just a little bit of the topology that comes in. Okay? Because we know that if you want to compute Betty numbers, what you need to get a hold of is these upper Koszul complexes, right? And the nice fact about these guys, and it's kind of the underlying combinatorial fact that allows you to prove things, is that the upper Koszul complexes here, in this case, are shifted complexes. And what that means is you have a simplicial complex where if you have a face, then you can always take out an element of the face and add a bigger element, and you're still going to get a face. So let me give you an example of how this looks. So for example, let's say that I put a face 3, 4. Well, that means that I can take out 4 and put in 5, and that should also be a face. So 3, 5 has to be a face. But I can take out 5 and put in 6, so 3, 6 has to be a face. Now, because 3, 4 is a phase, I can take out 3 and put in 5. So I get that 4, 5 has to be a phase. So the point is basically that if 3, 4 is a phase, then everything bigger than it has to be a phase. 3, 5, 3, 6, 4, 5, 4, 6, 5, 6. For example, if 3, 4, 5 was a full triangle, then all of the triangles bigger than it have to be full. Okay? But for example, if 4, 5, 6 is a triangle, then that doesn't really force any bigger triangles. Okay? And so this is what a shifted complex is. It's a shifted complex that's kind of bottom heavy, right? So where it kind of the smaller numbers have fewer things, the bigger numbers have bigger things. And the point is that the topology of this is very nice and combinatorial. You can say very explicitly what the homology of these things are just by combinatorics and without having to do any kind of topological computations. So because shifted complexes are so nice combinatorially